Now we move from the first order solution to the second order solution. The overall strategy is exactly the same as before. Since the unperturbed eigenstates form a complete orthonormal basis, we can expand the second order correction term to the wave function in that same basis as shown in this formula. So the summation runs over all states indexed by m. Also, we use the superscript 2 to indicate that the expansion coefficients are associated with the second order correction term. And of course, from the previous derivation, we already have the first order correction term expressed in the same orthonormal basis as shown here. So now we substitute these expansions into the second order equation. At this stage, the algebra looks longer than in the first order case, but conceptually nothing new has happened. We are again expressing everything in the unperturbed basis and then projecting onto a particular bra vector phi sub k naught. Once we do that, orthonormality simplifies the result dramatically. After projection, we obtain the equation at the bottom of this page. This is the key matrix element equation for second order. The unknown second order coefficient, a sub kn2, is now coupled to known first order quantities. That is exactly what we should expect. Second order perturbation theory is recursive. Once the first order coefficients and the first order energy shift are known, they fit directly into the second order equation. So the logic is very systematic. First, solve zeroth order, then use that to solve first order, then use those results to solve second order. Also notice that the equation contains two distinct cases, just as before. If we set k equals n, we will obtain the second order energy correction En2. If we set k not equal to n, we will obtain the second order correction coefficient a sub kn2 for the wave function. So the next step is to examine the two cases where k equals n and where k doesn't equal n separately. Now let's first consider the case where k equals n. Starting from the projected second order equation, we set k equals n, then delta sub n equals 1. These two terms on both sides, they are identical and can be cancelled. So the equation for the second order correction term to the energy of the nth unperturbed state becomes the one shown here. Now we decompose the summation over m into two parts. The m not equal to n terms and the m equals n term. Then apply the first order results we already obtained. Since we know that En1 equals h sub n prime, the first order correction term to the energy of the nth unperturbed state must equal the expectation value of the perturbation operator in the nth unperturbed state. The last two terms on the right-hand side cancel. We then substitute the equation for a sub kn1 back into this expression and replace k by m. We arrive at the result shown here. Now, since the perturbation operator is Hermitian, this equation must hold. So we can write the equation for En2 more transparently as shown here, where the denominator is the absolute square of the matrix elements of the perturbation operator in the unperturbed states. So this is the standard second order energy formula for the Nondegenerate case. We see that unlike the first order energy correction, which depends only on the diagonal matrix element, the second order energy correction depends entirely on the off-diagonal couplings to all other unperturbed states. So even if the diagonal expectation value of the perturbation vanishes, the energy can still shift at second order. This formula also shows how nearby states matter more strongly, because the denominator becomes smaller when another level lies close in energy. And the sign of each contribution depends on whether the state M lies above or below state N. So if the denominator is positive, the contribution is positive. If the denominator is negative, so is the contribution. So states above the nth state contribute negatively, while states below state N contribute positively. A particularly important consequence is that the ground state usually shifts downward at second order because all other states lie above it. This is one of the standard signatures of second order perturbation theory. Now we return to the normalization condition and use it to determine the coefficient a sub nn2, which is the component of the second order wave function correction along the original unperturbed state itself. The corrected wave function up to second order is written as shown here. We now impose normalization condition given by this equation and keep terms only to the second order in lambda. After expanding and using orthonormality, the normalization condition gives the equation shown here. From the first order treatment, we already adopted the usual convention that a sub nn1 equals approximately to 0. Then these two terms, they are gone. We end up with the equation shown here. Typically, a sub nn2 is taken to be real. This gives the result as shown in this equation. Then substituting the first order coefficients obtained previously into the equation for a sub nn2 and replacing k by m, we obtain the final result as shown. So physically, what does this coefficient mean? It is the coefficient of the normalization correction term along the nth unperturbed state. Why this term is needed becomes clear from the norm of the nth perturbed state, which has been shown in this equation. After first order mixing, the norm of the nth perturbed state is approximately given by 1 plus lambda squared times the summation term shown here. So the norm becomes too large unless we add a compensating second order correction along the nth unperturbed state. That is exactly what leads to a sub nn2. Therefore, the term shown here is introduced so that psi sub n remains normalized through the second order. Now let's determine the off-diagonal second order coefficients, that is, the coefficients a sub kn2 for k not equal to n. We go back again to the projected second order equation shown here. For k not equal to n, the quantico delta vanishes. So we obtain the equation shown here. Using the first order results obtained previously, we first obtain the equation for a sub kn2. Then replacing k by m and m by k, we obtain the equation for a sub mn2, as shown at the bottom of this slide. This expression may look formidable at first glance, but its structure is actually very instructive. The first term describes a two-step coupling process. The perturbation connects the original state n to some intermediate state k, and then from that intermediate state k to state m. So this term represents second order mixing through intermediate states. The second term shown here involves the first order diagonal energy shift h sub nn prime, and it acts as a correction that must be subtracted when the first order energy correction is already present. Now we collect all of the results and write the perturbed eigenfunction and eigenenergies up to second order, with the perturbation parameter finally set to 1. The energy is given by this equation. The first order correction H sub n prime is the first order energy shift coming from the diagonal matrix element of the perturbation. The second sum is the second order energy shift coming from off-diagonal couplings to all other unperturbed states. So the first order energy depends on the diagonal part of the perturbation, whereas the second order energy depends on the off-diagonal couplings. The wave function up to second order contains several contributions. First, the original unperturbed state as shown here. Second, the first order admixture of all other states. Third, the second order off-diagonal corrections through intermediate state couplings. And finally, the normalization correction along the original state itself. So although the final wave function expression looks long, it really contains only 4 pieces: the original state, the first order mixing, the second order off-diagonal mixing, and the second order normalization correction. Now let me emphasize the physical meaning here. Second order perturbation theory goes beyond simply shifting an energy level by the average value of the perturbation. It includes the indirect influence of all other states through virtual mixing. That is why second order terms are so important when the first order diagonal matrix element vanishes by symmetry. In those cases, the first order energy correction is 0, but the second order correction may still be non-zero and physically significant. So this final slide also makes it clear why the non-degenerate assumption matters. Every denominator contains energy differences such as E sub n naught minus E sub m naught. If one of those becomes 0, the entire non-degenerate derivation breaks down, and degenerate perturbation theory is required. So the big picture is now complete. First order theory gives us the leading energy shift and first order state mixing. Second order theory adds energy shifts arising from couplings to other states and refines the wave function so that both mixing and normalization are handled consistently.